Hello, everyone. It's 12 noon and time for our weekly GreenTalk. Welcome to all of you, and a special welcome to our speaker, Dr. Eugene Cordero. He's one of our own faculty, a climate scientist and professor in the Department of Meteorology and Climate Science at San Jose State here. A PhD he has from UC Davis. He's worked in universities in Australia and has research focuses on understanding the processes responsible for long-term changes in climate through the use of observation and atmospheric models, and is founder and director of a very special project called the Green Ninja Project, and he's going to tell you more about this and a lot of other great things. I'm going to turn everything over to him. Thank you. Let's give him a warm welcome.
How's that? Okay, that sounds great. So thank you for having me. I just taught a class. I just came over here, and I'm excited to be in front of engineering students who are going to be the architects of our future. So I'm going to talk to you about a variety of different things. We'll just get started. So this is me. I do have a PhD, so they call me a doctor, but I'm not really this kind of doctor, obviously. I don't carry a stethoscope. But on campus, for some reason, some people call me Dr. Burrito. And I'm not sure why. Well, no, there is a reason why. But I might see some of you later on, like walking around campus, that, oh yeah, that's the burrito guy. So I'm going to tell you a little bit about how that happened. And I'm going to kind of have you join me on a story about that journey. And that journey started when I was an undergrad at Cal State Northridge. And I was in a public speaking class. And you've all taken public speaking. And this was the final talk that I had to give. It was supposed to be the best one. So I showed the audience this. This is a chemical reaction, and this is chlorine plus O3, which is ozone. So I was thinking about the ozone hole. And it turns out that chlorine plus oxygen produces chlorine plus ozone, chlorine monoxide plus oxygen. And that chlorine monoxide can interact with oxygen to reproduce another chlorine atom. And this chlorine atom can then go and react again with ozone. And this thing can happen like 100,000 times. So one single chlorine atom can actually convert ozone molecule to oxygen. And that's called a catalytic cycle. And some of the chemies in here, of course, know this very well. But it turns out that this is what was responsible for the Antarctic ozone hole. And so that's what my talk was about the Antarctic ozone hole. And it turns out that I became an atmospheric scientist and started studying ozone, and I worked at NASA at the Goddard Space Flight Center with the largest group of scientists studying ozone depletion. And it was a great experience. And here's the ozone hole. So it turns out that ozone levels declined for this is the total concentration of ozone from the 60s through the turn of the century, ozone levels had declined. But the good news is that as scientists, we identified the problem, that there was these chemicals, and we decided as a society that we're going to phase out ozone-depleting chemicals. And so the projections are that for the future, that ozone levels are going to recover, that the ozone hole is going to recover. It's going to take a while, 30 or 40 years. And that's kind of good news. Actually, it's really good news because remember that ozone is the kind of shield that protects the planet from harmful UV radiation. If we didn't have an ozone layer, we would not be here. We would have no life on the surface of the planet. So this thin layer of ozone is actually super important. And when we saw that it was declining and that humans were responsible, we took action to phase out ozone-depleting chemicals. And so we're on track to kind of fix this environmental problem. Now, my colleague at NASA Goddard, Paul Newman, it's a different Paul Newman than the one you might have heard of, the actor, but has the same name. He developed this study where he looked at what if we hadn't paid attention to the scientists and the policymakers? What if we didn't phase out ozone-depleting chemicals? What if we said, oh, that's a hoax, or it's not really that important? What would the world look like? And that's something, a simulation that he calls the future world that we avoided. And this is how ozone levels would have changed throughout this century if we hadn't phased out ozone-depleting chemicals. So we would have lost more than 50% of our ozone in just a relatively short period of time. Now, what would the world look like? This is something called the UV index. It tells you how much UV radiation is hitting the surface of the Earth, and people use this for the exposure to getting sunburn. So this is a national product that comes out every day, tells you the UV index. Numbers like 8 and 10 are really high. That's very high. And extreme is above 11. Well, in this future world that we avoided, here's what the numbers would be like. They'd be above 10. They'd be 15 or 20 or 30 by the middle of the century. So what would the world look like? By 2050, an average person could get sunburn in less than 5 minutes. That might look like this, or hopefully not like this. And maybe we'd have to live like this. So this, though, didn't happen. And I'm going to share with you some things that I've learned since that kind of first class at Cal State Northridge. And in this case, the thing that I've learned is that small things can be important. The amount of chlorine, extra chlorine in the atmosphere that came from human activities is tiny. It's measured in parts per billion. And yet, it turned out that it affected our climate system in a very significant way. It depleted the ozone layer. And if we let it continue, we would have totally screwed up the planet. By 2050, it would be a catastrophe. And so it showed us that we inadvertently can have an impact on our climate system or on our environment. But fortunately, we could also remedy it. So it's actually a really interesting story in that case. But the small things, it's a small amount of chemical. So for example, just to kind of illustrate this point about small things, I'm looking for someone. Anyone have a water bottle? It's drinking like some water. I'm sure most of us are well hydrated. You have one? Okay, yeah, thanks. I'll just use it. I'll give it back to you. So you got this water. Oh, it's kind of cool. That's nice. Would you mind if I just put a tiny, tiny, tiny fraction of cyanide in there? There was a pause. Yeah, even just a tiny amount, right? We all know what cyanide is this some kind of horrible poison that, you wouldn't want to put. So, there are times when small things matter. And the ozone depletion case is one of those examples, and we can think of other cases. And yet, people who are not scientists and engineers often think, oh, it's just a little bit of pollution, or it's just a little bit of this. It can't really have an impact. The planet's a big place, right? And that's where science and engineering comes in, is that we quantify, we quantify the impact of things. Even though the person off the street might think, oh, that's not that important. The ocean's a big place, the atmosphere is a big place. This little pollution is not really going to have that big a deal. That's true in some cases, but not in all cases. So this is obviously the planet we live on. And after I did some research on ozone depletion, I actually spent a few years in Australia because it's close to the Antarctic ozone hole, and we were studying ozone. But we kind of figured it out. We said, okay, it's humans. Here's what we need to do. Policymakers took steps. So a lot of the atmospheric scientists that I work with, we moved on and started to study climate change. And this became, over the last few decades, the kind of primary subject of investigation. And the issue really is that the global average temperature of the planet was kind of constant from 1880 to about 1960. And then since 1960, the planet's temperature has really gone up fairly dramatically. And this is the latest data from the NASA Goddard Institute for Space Studies. And other observational networks also see similar results. Now, you notice the temperature doesn't just go up every single year. It fluctuates a lot, and that's to do with oceans, and that's to do with changes in the sun, things like El Nino. But you can see that there's a very pronounced trend, especially since around 1970, of warming. Now, that additional warming of the planet, although this is measured in 0.2, 0.4, 0.6. It's been about 1 degree Celsius or 2 degrees Fahrenheit. May not seem like a lot, but if you look at, for example, these glaciers in Norway in 1918 and you compare them to today, you can see that the amount of ice on the planet over that number of years has really gone down significantly. And here's another example in northern Alaska in 1922. And then today you could see this large glacier, because of this additional warming on the planet, has gone away. Now, actually, I find this especially remarkable because this little iceberg right here, it's still there, 85 years later. Yeah, of course, that's a joke, right? That's a different iceberg. But the amount of ice on the planet is declining. Here's an image from 2012. The yellow line here is what's normal, and then this is the amount of ice in the Arctic in that particular year. And it turns out that this amount of ice is going to continue to decline. And there might be some good results as a result of that, is that you might be able to take a ship and move it across, instead of going across the Pacific or the Atlantic, you can take a shortcut over the pole. But one of the kind of bad things about this is that this is normally a very reflective part of the Earth. It reflects incoming light from the sun. And now if you replace it with dark ocean, you're going to add an extra heat. And so this is kind of like the planet's refrigerator. It's keeping the planet relatively cool. And if you get rid of that, it could accelerate the warming, which isn't really a great thing. And we are seeing that September Arctic sea ice is going down. This is just the record from this year. And you can see a very strong trend. And you don't have to be a scientist or engineer to figure out that eventually we're going to have ice-free summers. And there's lots of implications for that. One of them being that storms across North America might start to move across slower. And one of our alumni from San Jose State is become kind of internationally known for looking at how weather systems move across the United States and the relationship with Arctic sea ice in the summer. It's interesting stuff. Now, we have been dealing with climate and weather disasters for many years, but here's some data from the last couple of years. 2016, we had 15 weather and climate disasters that cost over $1 billion in damage. We had very large drought. We had flooding all across, and this is 2016, all across the Central Plains, especially Texas. We had a hurricane, and this is something that just we've seen over and over, but it's really costing the country real money. In fact, last year, we don't have the final results, but last year was over $300 billion in damage due to weather and climate-related disasters. Hurricane Harvey, Hurricane Maria, and Irma, really expensive. Then we had, and we basically only have some of the fires that we had in California. So we're actually starting to really pay for this right now. Now, a good question that people could ask is, how do we know what's causing this warming? It's very clear the planet's warming. We see the ice melting. We see species migrating. We see these storms becoming more intense. But what could be causing that change in climate? Now, it could be the sun, and the sun could have gotten a little stronger. It could be due to volcanic eruptions. There's lots of there's a variety of natural factors that could be affecting our climate system. We study these things, and that's what we've been doing for the last 50 years, is studying natural climate change. What are the natural factors? But we also study what role humans are playing. And the end result is what we have found, and I'm going to show you some data to support this, is that the rise in carbon dioxide, this is a gas that is released when you burn oil or gas or coal, that the rise in carbon dioxide is the primary contributor to the recent warming. And this is not my idea. This is the idea that comes from a large base of scientific inquiry. So this is from the Mauna Loa Observatory from 1958 through to close to today, and we can see the very steady rise in carbon dioxide. Now, there's various lines of evidence that look at, what is the human contribution to this warming that we see. And I'm just going to share with you that there are, let's say, 4 kind of general classes that scientists use to try to understand the human connection. Because we really, just like in your engineering field, like if you make a mistake, it's bad news, right, as an engineer? Well, maybe if you're designing a software app and it's a game or something and they don't get the points that they deserve or something, that's not such a big deal. But if you're a bridge engineer, you're designing an automobile, something that deals with people's lives, it's a really big deal if you make a mistake. Same thing in science, we feel, that we don't want to make mistakes. So we're very, very conservative. It takes a long time for us to kind of believe something. So these are the different tools that we use to try to figure out what's causing the climate to change. So I'm going to show you what the radiative forcing kind of looks like. It's an energy bookkeeping type of tool. But we use these climate models that predict the past or the future, and we can run these different experiments. We do this thing called fingerprint attribution and detection. It's kind of like detective work. And we actually measure how much energy is coming out and going in, and we just keep track of it almost identically. I'm going to show you the radiative forcing because for engineers, this could actually be valuable for you. Because if you understand this chart and the implications of this chart, you might be able to design a solution to climate change. And actually, if you design a solution to climate change that could even produce 0.1 watt per meter squared improvement, you have the ability to make a ton of money. Because ultimately, we're going to see a carbon trading scheme, an international carbon trading scheme that is going to reward companies and individuals who can reduce the impacts of climate change. And this diagram provides really interesting insight into how to do that. So what this diagram shows is factors that are changing our climate and whether they make the climate warmer or cooler. And they quantify them. And they're in units of watts per meter squared. So a watt, it's a unit of power over a square meter. And it turns out that only like 1 or 2 watts per meter squared are responsible for changing the temperature of the planet by a degree or so. So it's actually a pretty big deal. And 1 degree temperature change, we're noticing $300 billion in damage because of 1 degree temperature change per year. So yeah, it's a big deal. So what this says is that carbon dioxide and other greenhouse gases are warming the planet by a certain amount. This says that other ozone, and this is really air pollution, are also warming the planet, although stratospheric ozone loss is cooling. There's some other things going on that we're also seeing black carbon aerosols, these little particles in the atmosphere. They're warming the planet. But we're cutting down trees, and we're making the planet brighter. That's actually cooling the planet. So we actually have 2 things going on, both warming and cooling. And then when we add these aerosols, little particles in the air that you see coming out of factories and your tailpipes of automobiles, they're reflective, and they're actually cooling the planet. So in fact, when you drive a car, you're doing 2 things. You're emitting carbon dioxide, which you can't see, and that's warming the planet. That's here. You're emitting aerosols, the little particles that you see coming out, the exhaust, and they're cooling the planet. And this tool allows you to compare which one is stronger. And then there's also the sun, and the sun is getting a little stronger. This is a natural factor, but you can see it's far smaller than any of the other factors. And then when you add them all up, add up all the human contribution, the warming is kind of beating out the cooling. And that's why we're seeing the planet warming. We don't know that, you wouldn't know intuitively that we're also cooling the planet or trying to cool the planet, but it's being overwhelmed by the warming due to carbon dioxide primarily. So here's where the engineering comes in. If you can figure out a way to change any of these things, for example, to make carbon dioxide have less warming, or maybe you look at methane or NO2, and you're able to change these. Methane is coming from natural gas. There's a lot of leaky natural gas pipelines. That's one of the sources of methane, also from cows and other ruminant animals. So some engineers are working on, could you feed cows something different so they don't burp as much methane? And if you could do that, and if you did it at scale, you might be able to reduce the 2nd largest greenhouse gas. And you would make a ton of money. You really would. So, because this is related, this is happening now, it's costing us financially. People are trying to figure out what to do about this. So this kind of tool allows us to do a couple things. One, it quantifies what the human impact is on a climate system compared to natural factors. The only natural factor here is the sun, and it's small compared to everything else. But it also allows us to look at the various different things that are going on. Another engineering strategy might be, could we make these larger? Could we make these negative ones go even larger? Like, could we put some aerosols in the upper atmosphere and they hang around for a few years reflecting incoming sunlight? Could we artificially produce more clouds? If you could figure out how to do that, you're going to cool the planet and keep the warming level lower. Those are called geoengineering approaches. And at the conferences I go to, there's now whole sessions of people doing geoengineering simulations in climate models. And I expect the engineers to be involved too, saying, oh, what if we tried this, or what if we put these giant mirrors in space, or something like that. So that field of geoengineering, although, to be honest, the modeling simulations show that if you geoengineer the planet to make it cooler, there's a lot of winners and losers, but there's a whole bunch of losers. Like in one simulation that my friend ran, they put some aerosols in the upper atmosphere. They use rockets and fire these aerosols, little particles, cools the planet by about 2 degrees, like fast, in a few weeks. It stopped raining in the Midwest. Like it totally changed the weather patterns because we're changing the whole heat distribution of the planet. And the Midwest, which normally gets rain for the corn and soybeans, didn't get any rain in his model. And so you can imagine some people grumpy about that kind of thing. In fact, the military is quite interested in geoengineering. Can they change the weather? And we've largely been unsuccessful at that because it's so random. It's hard to figure it out. It's a highly nonlinear problem. So the end result is that we need energy for electricity, we need energy for transportation, we need energy for food, and that today, most of that energy is generated by burning fossil fuels, and that produces carbon emissions. And then the carbon emissions change the climate. This is kind of like the simplest illustration of the problem we're facing today. And the reason that I like to come and talk to you folks about this is that in this classroom, you have the ability to try to change this in some way. Either to make this more efficient and not use as much energy, or to change this energy so that there's not carbon emissions, or to figure out how to grab the carbon and stick it back in the ground so it doesn't change the climate. There's various places where you can try to interact with this. But if we don't interact with this, then we should be aware that the predictions for the future really don't look that good. I'm not going to kind of say, oh, it'll be all right, because I actually don't think it will be all right. So here's some climate model projections for the last 150 years, or last 50 years. And then here's a whole set of possible projections for the future. This is how temperature is going to change. And they have these different scenarios. We don't know how temperature is going to change because we don't know what kind of energy we're going to use. We don't know how many people are going to be around. We don't know if we're going to adopt renewable energy or we're going to stay burning fossil fuels. So they have these different scenarios. This red one is the business as usual scenario, where we just basically keep doing what we're doing. And it shows that by the end of the century, that the temperature is between 5 and 6 degrees Celsius warmer. That is not a good planet to live on. Not with 10 billion people on the planet, having access to water and food. We would definitely see significant impacts on the global economy. We would see significant impacts on agriculture, real pressure on coastal regions. It's like we just can't let the planet get like that. Otherwise, we're bound to see very significant changes in our society. They wouldn't be good. Lower emission scenarios are better, but the United Nations over the last few years has decided that 2 degrees would be the kind of highest target we should go for. And they had this Paris Agreement where they set 2 or even 1.5 as the real target. And so there is a scenario here that stabilizes climate and moves on to renewables very quickly. I'm going to show you a little bit more about that because a report just came out a couple weeks ago. But this is what the international community is looking at, is how do we get on to a more climate-friendly trajectory? Because these others are not going to be good. And remember how we did something about ozone depletion? Well, we've known about this for some time, But we haven't been making much progress. So here's one of the challenges. The carbon emissions that we have been putting into the atmosphere, we've basically taken fossil fuels from the ground, and we put 1,500 gigatons of carbon into the atmosphere over the last 150 years. And it was great. It was a good investment, right? Everything we have here came from burning fossil fuels. The seats are made from petroleum. They come from plastic. The energy for this whole thing is coming from natural gas burning. Your clothing is primarily fossil fuel product. Even if you say, oh, I have a cotton shirt, that cotton was farmed with oil and gas. We live in a fossil fuel environment. And that has benefited us a lot. That's why we can support 7 billion people here on the planet. But as a result of that, 1,500 gigatons of carbon in the atmosphere, and we didn't know this until a few decades ago, that has caused our climate to change. And if we want to keep 2 degrees as our upper limit, then according to estimates, we can only burn another 500 gigatons of carbon. Like that's as much, so we can't put another 1,500, it would be way, way over, unless we can figure out some other approach. It turns out there's about 3,000 gigatons of carbon in the ground right now. And oil and gas companies own about half of it. And they want to burn it. That's what they do. That's how they make money. And at the current rate, we have about 15 to 25 years before we put this amount of carbon into the atmosphere and before we're pretty much assured of going over 2 degrees C. So we actually don't know, we actually know like how much time we have. So that's the challenge that we face, is that we don't have 100 years to figure this out. We have a decade or two to figure this out. To really start to change this carbon trajectory, which is just going up every single year, we have to do something to change that. So in terms of things that I've learned, the second one is that we have to keep carbon in the ground. We can't keep burning fossil fuels. We've got to leave it in there. Or if we do burn it, now onto engineering, you've got to figure out how to grab it and throw it back down, or turn it into a rock, or use it some other way. But we can't let it continue to warm the planet. So how do we do this? Well, renewable energy is going to be, is really growing fast. This is urban renewable. This is Todd Pellman, who developed he's an engineer who developed a urban wind turbine. This is offshore, large-scale wind. This is a solar farm in the southern deserts. These are actually mirrors that just shine light onto a heat engine right here. So kind of low-tech, high-tech. Interesting, because it's not using solar panels. These are just mirrors that follow the sun. This idea of concentrated solar power is a good engineering technology. Electric vehicles like this one certainly make a lot of sense. And so do reverse cycle heat pumps. This is another way to heat your home, just using electricity. And a bicycle. All of these can be evaluated and should be evaluated using science and engineering data. And in fact, my friend is the bicycle planner for the city of San Jose, John Brazil. And we were talking about bike lanes recently. And so here's a bike lane on 10th Street. And someone said, I don't think bike lanes are a good idea because normally you had a traffic lane and cars move along faster if you don't have a bike lane. And then when cars are slower, they emit more pollution. So I mentioned this to John. I said, do you ever have people push back on you about building bike lanes? And he said, we actually do the data analysis. Before we can build a bike lane, just like any good engineer, you have to do an environmental impact analysis. And you're going to end up doing these in whatever career you have in engineering. So we have to see, when we do this new change, adding these bike lanes, does it impact, what is the environmental impact of that? And they count how many cars go through with 2 lanes versus how many cars go through with 3. Is there really additional traffic? When you add it up over the whole year, what's the impact compared to what the benefit is? So this cost-benefit kind of analysis. And he said, we found that on 10th Street, just here, when we put the extra bike lane and reduced the car travel lanes, that at rush hour, it delayed cars, only that 1 hour of rush hour delayed cars by 36 seconds. This is pretty minimal. So 30-second additional time. And the city was happy with that and to promote people moving other ways. So as engineers, you're going to have to look at the data. And so we need to do that. When we're designing solutions, climate change, we need to look and see, like, does it really make sense? That's the way the scientists and engineers will do that. And in this case, we see that it definitely makes sense. So use data to inform your impact. So I'm going to offer to you a 3-step plan for how to get on a low carbon trajectory. And if there's one thing to remember from this talk, I would hope it would be the 3 steps. So the first step in terms of, and this would be international, but we could apply it at a local level too, is reduce energy demand. So make things more efficient. Make your cars more efficient, your housing and heating and cooling more efficient, make the agricultural system more efficient to run your computers and your phones, make it more efficient, use less energy. And if you ever get solar installed on your home, in your homes in the future, which I imagine it will happen to many of us, the first thing the solar installer will say to you is reduce energy demand before you size your solar system. Change out your light bulbs, get a more efficient refrigerator, do everything you can. So that's step 1. Step 2 is to electrify everything. Heating, cooling, transportation, everything's got to have a plug. And in fact, the Bay Area Air Quality Management District, in their plan for 2030 for the Bay Area, says that all new construction in the year 2030 will not have natural gas. No more natural gas to your home. So you're not going to heat your home with natural gas. You're not going to have when you turn on, if you have a gas stove, you see a flame. Yeah, it's burning natural gas. It's putting carbon into the atmosphere. So we will see that go away. Because even though natural gas is better than coal, it's still a fossil fuel. So electrify, that would mean cooking and heating with electricity. And then the last step, which is critical, is get your electricity from renewables. So electrify everything and then get your electricity from renewables. If you do this, if we can do this as a society or as a city or even as an individual, we can significantly reduce carbon emissions. And I'm going to give you an example, a very personal one. So this is where Claire and I live. So Claire, my wife, is a 100W instructor. Some of you are in her class. So this is our home. And when we bought this home, it's a nice little suburban home, we decided to do an energy efficient remodel. So we decided to adopt this 3-step plan. And we actually have we're going to show you some of the data that goes with it. So the first step is reduce energy demand. And in fact, Claire, being smart, she said, I wanted to install solar panels first thing. I like technology. It'd be fun to have solar panels. It's our first house I've ever owned. But she said, it seems like we use a lot of energy for heating. Heating doesn't sound like fun. It was an old furnace. But it turned out she was right. We used a lot of energy heating. So we insulated our home. We used this thermal insulation. It's basically like cardboard and jeans, and it's a fiber. And we hired these folks to blow it in our attic, and they insulated the bottom of the floor, and then they cut all these holes in the walls. So it's fairly intrusive, and then they just dump the stuff in there. That's how they insulate the walls. And here's a kind of a so you can see the fiber right there. And here I am. Luckily, this is just a stroke of luck. When they were doing this, my colleague, Craig Clements, did he speak here this semester or no? Okay, he's spoken at this before. He's a fire weather guy. He got this $100,000 FLIR camera that measures infrared radiation. And I saw it in his office, and I said, oh my gosh, Craig, can I borrow this thing just for a night? I want to see how well these insulators are doing. So I had this camera so I could take photos like this. So you start to see the thermal signature of this, and you could see that we're getting a lot of heat, but you could see the holes. And here's I'm looking at the ceiling, and you can see the rafters and the insulation that's being applied there. Oh, and here's our general contractor. I don't know why I took a photo of him, but I was interested that this region was very, very warm. So you learn something interesting with these tools. But then, the morning I was going to give back the camera, I went into the bedroom, and I noticed this. And I was like, ooh, So what's going on here is their sun is shining on the back of this, on the wall, and then it's being heated. And they had halfway done the insulation, they hadn't finished. But what they've been doing is drilling holes here and dropping the stuff. Well, apparently there was a diagonal beam here. And so when they dropped it, it dropped like here, but it didn't go down here. And since they don't have a thermal camera, they couldn't tell, right? So the insulation, they blow it in, it dropped, but this diagonal piece of wood was blocking the insulation down here. And I was able to send them this photo and say, hey guys, drill a hole right here, put some more insulation, and otherwise we're going to have a gap. So that was pretty cool. We also installed energy efficient windows, so we changed out those windows to double pane windows with argon gas in between, have really good insulative properties. So we tried to reduce energy demand as much as possible. Step 2, we electrified everything. So we took that gas heater that wasn't really that great, used a lot of energy, and we replaced it with a mini split reverse cycle electric heater. That's cooling as well. If you go to Asia or other places, you'll see these 4 times as efficient as an electrical resistance heating. So actually a pretty efficient way to heat your home. We also installed solar hot water. And here they are installing the solar hot water. It's a 40-gallon tank of water that's basically just some copper pipes painted black. Super low tech, kind of like putting your garden hose on your roof. And we don't need to heat our water for about 6 months of the year. When it's cooler and there's not as much heating or as cloud, we have an electric flash hot water system to bring the temperature up to whatever we want. So it's a nice system for the water. And then the last step was get your electricity from renewables. So finally the solar panels came. I was excited. SunPower, local company, with microinverters. For those of you double E's, you might know what these things are, converting from DC to AC. And then here's the solar installers. I don't know why, but solar installers always have their shirts off, or if they're guys, they do. That's just, it attracts a certain type of person, and this is very kind of classic. So we installed this system. It's about a 4 kilowatt system, and here's the solar hot water system. And the nice thing about having the microinverters is that there's an inverter on each panel, so you can see the performance of the system every panel by panel. And if one panel drops, the solar company will call us and say, oh, you might have a problem with your microinverter or something like that. Pretty cool. Anyhow, okay, that's all fluff. You guys are engineers, you want data, right? You want to see, like, show me the numbers. Okay, so here's how much energy in kilowatt hours per day that we were using pre-remodel. So you notice that Claire was right, that the energy use in the winter was like 4 times higher than in the summer. That's because of heating. So you can see the big amount of energy in summer, and some winter. In the summer, we didn't use as much. So we lived in the house a couple years before we did the remodel. And then here's how, so this is before, and then here's how it changed afterwards. So this has nothing to do with solar. This is just solar hot water. This is insulation, primarily insulation and solar hot water. Reduced our energy demand by almost 4 or 5 times. So that was step 1. So that was pretty good. Then we, and this is a graph of that where I took a running mean or something like that. So this is how much energy we used to use, and now it changed to this. Then we started looking at our solar. So this is a number of years of solar production being highest in the summer and lower in the winter. So we produce about between 15 and 20 kilowatt hours of energy per day. So this is how much we're using, about 7 or 8 or 9 kilowatt hours per day, and now we're generating, more than that. In fact, we oversized the system. We really weren't sure how low this would go. It was hard to figure that out. And then we also thought that we might buy an electric car and that this could account for some of that. So turns out, though, right now, we're saving about $800 a year in electricity costs. In fact, the electricity provider will pay us that money because we're overproducing in terms of our electricity. And it's possible the time will come where people will put as many solar panels on their roof as possible because there will be a payback for that. And that certainly happened in Europe. And in Germany, they pay 50 cents a kilowatt hour, and so people will fill their roof with solar panels because they actually can generate money. They're a small power plant. And imagine having thousands or millions of small power plants. That's the way you could provide energy to a city. So our answer to all this is the three-step plan. Can you do it at a local level? We found that you could. Now, in 2008, I co-authored a book about food and climate change. And I still am, a scientist who was friends with this woman, Laura Steck, who is a foodie. She's a chef. She's an environmental food activist. And she decided to write this book. And it kind of led me to start thinking about my own life and my own carbon emissions, even before the remodel. It was kind of like earlier on. And I started thinking about things that I enjoy. And so here's two things that I enjoy: bicycling and burritos. In fact, the burrito one I really like. So I created something called the Burrito Enjoyment Index. And I looked at the average American, and I compared it with myself. And I found that indeed I'm like especially interested in burritos. And so I started doing these burrito calculations. Like I started calculating the carbon footprint of different types of burritos. So for example, I compared a chicken versus a beef burrito, and I was shocked to find that a beef burrito, which doesn't cost any more than the chicken burrito at my favorite burrito place, which is La Victoria, which hopefully many of you know, that there isn't really a big price difference, but the carbon footprint is about 5 times larger when you choose a beef burrito compared to a chicken burrito. And the reason is that cows are very poor converters of energy into food. Like a chicken is just, you grow a chicken in like 6 or 8 weeks, you can eat it. A cow takes, almost 1,000 days to do that. Cows also are ruminant animals, so they have their stomach, this thing going on. It's basically like just putting a whole bunch of stuff and let's sit there. And then it starts to compost without oxygen and anaerobic digestion and produces methane, which is a greenhouse gas 20 times as strong as carbon dioxide. So there's some technical reasons why that's different. But I started to look at driving as well. And you could drive a regular car, like a gas guzzler as they call it, get 12 miles per gallon. You could drive a Prius and get 50. And it's kind of similar with diet. It's like you can eat more kind of carbon friendly, or you can kind of eat the normal diet. You can have the same influence. So in our book, we reported that driving and eating have about the same carbon footprint, and that you can make the same reductions in carbon footprint. You could buy a Prius, or you can eat chicken or more vegetarian and have a similar impact on our climate system just by the decisions. Now, what about bicycling? So what's the carbon footprint of riding a bicycle? Someone said 0. Someone else? Yeah?
Maybe also the carbon that's needed to make the bike?
Okay, so that's a good point. So you could look at the carbon that's embedded in this, that was required to make it, just like you would with the cars. But if we're just thinking about, yeah. Exactly. How many burritos? Thank you. So it depends. The fuel for a bicycle is your food, right? And so it actually depends on your burrito or how many. And it turns out that the fuel economy of a bicycle is as low as 75 miles per gallon all the way up to 500, depending on which burrito you eat. So if you're fueled by chicken burritos or veggie burritos, you're at the 500 miles per gallon. It's super efficient. Whereas if you're fueling yourself with beef burritos, it's not as efficient. So we were telling these stories and other stories about this interesting world of food. And I like talking about food because we interact with it at least 3 times a day, but it's super complicated too. Like, what should you eat? Like, what's healthy? And what's the environmental impact of the food that you do eat? And that's some of the stories we told in this book. And I gave, let's say, 100 talks in a year about this. Laura and I would go and talk to folks like yourselves and go to bookstores. But there was one group of folks that we didn't get to talk to, and that was young people. And we decided that at some level, we wanted to share solutions to climate change with younger folks. And so here at San Jose State, we kind of turned that story into a project which is called Green Ninja, and this is a Green Ninja character. And we started making, and this is almost 10 years ago, we started making films. We made a couple games with some software engineering students here at San Jose State. We have the Green Ninja Film Festival, an annual event where students make their own films. And so we've been doing this for about, let's say, 8 years. The general idea is to try to create an interest in activism in young people. And we decided to look at students because, for example, in this paper, Lasniak and Palin show that children average a purchase-influencing attempt every 2 minutes when shopping with their parents. So you can imagine a little kid shopping with their parents and they're like pulling on them like, I want that thing, right? Or you know, I like Fruit Loops or whatever it is. So, you know, kids can have an influence. And, you know, these kids who might become interested in doing something good for our planet can become activists, like at the Global Action Climate Summit, or could become engineers who are working on the Spartan Superhighway. And some of you might be involved in this project who's trying to produce a low carbon emission way to move around. So this is a primarily San Jose State team of scientists, artists, engineers, and educators. We have funding from the National Science Foundation, from NASA, from private companies, and we've just been building a new science curriculum, middle school science curriculum. Our goal is to have kids grow up learning about some of the things I've shared with you today, and more importantly, what to do about it. We're creating a whole bunch of different products. One of them is like a Fitbit for environmental education. It would be a tool that would allow a student to measure the environmental impact that they're having or that their family is having. And we're testing something about a transportation app right now where people can monitor their transportation behavior. We're also looking at augmented reality and how students can like look at their city and the design of their city and notice parts of their city that are well designed and parts of their city that could be improved. And we also have something called the Green Ninja Show, which is a series of videos on YouTube. And in the Green Ninja Show are videos of me, Dr. Burrito. Here I am interrogating some burritos. This was filmed at Iguana, so not at La Victoria, with my burrito meter. And it can tell the carbon footprint of these different burritos. And then here's another Dr. Burrito episode. This is you probably haven't seen where the Chipotle burritos come from, but this is a burrito farm. This is where they grow. And here I am pulling out, I don't know if you've ever seen the roots. You know, they cut them off so you don't see them when you buy your Chipotle burrito. But here's the roots on this burrito. Just look at those. They go down like, you know, like 2 feet. Of course, that's a joke. But we intentionally are using humor to discuss an actually kind of depressing subject, like the state of our environment and the future that, you know, is not necessarily that rosy. So we deliberately use humor. Now, there's actually a lot of better Green Ninja videos that don't feature Dr. Burrito. But, you know, our goal is to produce verifiable reductions in carbon emissions through K-12 STEM education. And we actually have some data to show that that might be possible. But the reason education is so important is that if you say to people, what choices can you make to reduce your contribution to climate change? A lot of folks are going to say, oh, I could upgrade my light bulb, or I could recycle, or I could, you know, do stuff like that, which has an impact, but it's what we call low impact. Medium and moderate impact things would be like hang drying your clothes. Oh, this is from a paper that just came out last year. Recycling, replacing your car with a hybrid. Those are moderate impact. But if you want to have a big impact, then you do stuff like eat a plant-based diet, switch to an electric car, buy green energy, avoid one transatlantic flight, live car-free, or have one fewer child. These are the things that are actually very impactful. So, of course, we want people to recycle, we want them to change light bulbs and do that stuff. But ultimately, we need to move our society to thinking about, you know, a different way of living. And this is why we think education is so important. And in our analysis, we've done an actual study that's in peer review right now. And we find that in addition to rooftop solar and offshore wind, electric vehicles and insulating all these kind of engineering approaches, that education can actually be just as impactful if it's done at scale and if the education's done right. And that's kind of what we're trying to do at Green Ninja. So we've been doing this research here at San Jose State on student motivation and engagement. We started a company in 2016 called Green Ninja, and we're just about to be approved as a publisher in the state of California. and for middle school science for grades 6, 7, and 8. And we're trying to get our curriculum into as many schools as possible. If you have any school district colleagues or friends or parents who are looking for a new science curriculum, send them our way. So in terms of other things I've learned, it's about dreaming big. Like, we have a big problem to solve, and we have to dream big. So the last thing I'm just going to share with you is the path forward. This report came out from the Intergovernmental Panel on Climate Change 2 weeks ago. It's called Global Warming at 1.5 degrees C. Remember I said the 2 degrees was kind of like the target? But actually, all the Pacific Islands were like, we need 1.5, otherwise our islands are going to be gone. So they looked at what are the probability of us getting to 1.5. And this was one of the most bleak reports that I've ever read from the Intergovernmental Panel on Climate Change. And they really offered kind of like these two perspectives. Is that, this is our planet, and, which one of these do we want to face? Do we want to, try to deal with? In their report, they said that we have 12 years to change our carbon trajectory, to have a good chance to get to 1.5. But they offered a path for that, and I think you'll find it interesting, especially the engineers in here. So here's our emissions of carbon, and this is today. They basically are saying, you got to stop putting more carbon in the atmosphere than gets taken out, like in the next 12 years. And then we need a rapid decarbonization. Rapid decarbonization is actually super exciting because it means everything in our society is going to change. Like I said, about your homes, about your transportation, about how we deal with energy. It all has to change if we're going to see this rapid decarbonization. And in fact, this was the first time I'd ever seen this in an international report, we need negative emissions. It's not just enough to reduce emissions to zero, they have to go negative. We have to start sucking carbon out of the atmosphere. If we have a good chance, the temperature is going to overshoot, but it'll come back down to 1.5 degrees. So this idea that I've been kind of looking at in terms of geoengineering for the last 10 years is kind of like, oh, I don't see us doing that. And a few years ago, you had some GreenTalk speakers come in and talk about some technology for taking air and sucking, like a vacuum, and grabbing the carbon and turning it into something else and throwing it into the ground or something like that. It's really, really hard. No one's figured out how to do it. Even George Bush talked about carbon capture and storage. Can't do it. Can't do it at a cost that makes any sense or that doesn't require more energy than it saves. We haven't figured that out. If we could figure out a way to suck carbon out of the air and bury it so it doesn't, there's a great way is to plant a tree. It sucks carbon out of the air and puts it in the tree. But then you have a forest fire and the carbon just goes immediately back. So if you can think of a good way to do that, but maybe use photosynthesis as a tool, they call it biomimicry, then we're going to need to do that. According to this latest report, we need to get into negative emission territory by the end of the century. So this is a challenging kind of landscape to be in, especially in the kind of Trump era that we're in today. And we have a president who doesn't believe in climate change and brings in other people to head the EPA and Department of Energy and Department of Interior who also don't believe in climate change, who are changing the laws and regulations in our country to make it more difficult to reduce carbon emissions, or to say that carbon emissions aren't really a bad thing. So for me personally, and I think for all of us, we have to be strong and determined. But I do believe we can do this. And this is the only planet we have. And just know that the scientific community has said that here is the big problem. And it's going to be engineers and policymakers who are going to figure it out. You have to develop the technology to enable this. We have some of the technology already, but the more compelling you make the technology, the cheaper you can produce energy, the more efficiently you can take carbon out of the atmosphere, the more efficiently you can drive an automobile or a washing machine or a tractor, the easier it's going to be for us to transition into this low carbon transition. And that's our real challenge. And actually, I believe that in every area of engineering, we have areas to contribute. Software engineering, mechanical engineering, electrical engineering, systems engineering, all of them. And if we make them more efficient, the cost is going to go down. In fact, at the Global Climate Action Summit a few weeks ago, it was mostly business leaders there saying, we're moving on this path because it's saving us money, because it makes smart decisions. So anyhow, thank you for your time. Good luck in your engineering careers, and I hope you consider climate.